Hello and welcome. My name is Elhelw, and today we're going to be continuing our discussion about indexes. I wasn't planning on making this video after the series of videos that I did on indexes before, but I received a bunch of questions in the comments, which I have tried to answer most of them, but I figured it might be better to make a video and answer these questions so that everyone can benefit from the answers. I will also put the links to the original videos in the description, so please take a look at those if you haven't already, because that may help you in understanding some of these topics. All right, let's start with the first question. The first question is, what is the difference between primary key and row ID? Are they the same thing or are they different? And if they are different, which of them do we find in the index? All right, so the easy answer is they are different. Row ID is something different from the primary key, and I'm going to talk about the differences here. So the primary key is a user-defined attribute or set of attributes. So this is one or more of the attributes in a given table. So when you're creating the table, you say create table, these are the attributes, and then you designate one or more of these attributes as the primary key. So that's something that is created by the user. The row ID, on the other hand, is a system-generated identifier, something that the system maintains and generates and deals with. It has nothing to do with the creation of the table or the kind of the user designating what is the row ID. That doesn't work that way. In many cases, the primary key has a real business meaning. It maps to some real piece of information. For example, if you're talking about, I don't know, shopping orders, you might have every order has a number. So the order that you see in the database is the same order number that's printed on the piece of paper that has the order information. If you are talking about employees, for example, each employee has an ID. So like this ID is the primary key. It's the same ID that is used in other documentation and so on. So usually these primary keys map to something else outside of the database. The row ID, on the other hand, is completely internal. It has no real world use outside of the database. It's only used internally. The primary key is often used to enforce the entity integrity, which in the case of the primary key mostly means that making sure that every entity is unique and has a unique identifier that can identify this particular entity. The row ID, on the other hand, has nothing to do with that. It's used for retrieval of tuples from storage. So it has the information necessary to be able to retrieve that tuple from storage. The values in the primary key are user-defined values. Since it's a user-defined construct, the values are also user-defined in most of the cases. Like usually when you're entering a new tuple, you enter the primary key value. There are some special cases where it's attached to a sequence or something that generates incremental values, but it's still a user-defined thing. You just have a tool that generates it for you instead of you entering it manually. The row ID is something that usually encodes the physical location of each tuple, things like the page ID, slot ID, and so on. Last but not least, the user can change the primary key value, assuming there's no foreign key that's pointing at it or something. If you enter a new row that has a primary key value, you can easily update that value to a different value. Again, and also assuming that it's still unique, like no other rows have that same value, you are able to modify it. You cannot change the row ID of a given row. That is something that depends on the physical location. Again, it's completely maintained internally by the system. The user has no control over it. So these are some of the main differences between the primary key and the row ID. Which one of them appears in indexes? That was the second part of the question. Potentially both, depending on the index. Any index, and I'm talking about the database indexes that are visible to the user in the query engine. Usually these indexes map from an attribute value or set of attribute values to row IDs. So the key of the index is usually attributes, and then the value of the index is the row ID. So you search using some attribute values, and when you find it, you also get the row IDs that you can then use to retrieve the tuples. So in that sense, row IDs are found in the index. This is the thing that you find in the index, and you take that to retrieve the tuples later on. And then what you search for are usually attribute values that may be the primary key. Like if the index is created on the primary key column, then the values that you're searching for are those, primary key values. So they both exist, or they may both exist in the indexes, but in different roles. All right, the second question is, could you please explain bitmap indexes? Just wanted to note something in the beginning. Bitmap indexes are different from using bitmaps to do something like index intersection or index union. We have talked about intersection and union in the past, and we've said that there are multiple ways to implement that using sorting or using hash or using bitmaps. So that's one thing. Bitmap index is something else. Bitmap index is a type of index, same or similar to like B-tree index or hash index. So bitmap index is a third category of indexes. So yeah, just wanted to kind of like make that note so that there's no confusion between the two cases. So yeah, we can talk about bitmap index, explain what they are, how they're built, and how they're used. But before I do that, I want to talk about a term called cardinality. Cardinality is a term that's very common in databases, and it may mean one of two things depending on the context. If you're talking about the cardinality of a table, then this means the number of rows in the table. If you're talking about the cardinality of a given column or a given attribute, then this means the number of distinct values in that column. So let me illustrate that with an example. Suppose we have this table orders that has 5 attributes: ID, order date, amount, status, and region, and the ID attribute is the primary key. As you can see, it's underlined. This is a sample of the data in the table. You have multiple rows. Each row has ID, date, amount, status, and region. And let's just, for the sake of the example, say that we have 1,000 rows in this table. There's a bunch of other things that we know about this table. For example, we know that there are usually less than 10 orders per day, so this is the orders table. We also know that status can only take one of 3 values, either P for pending, A for approved, or D for denied. Region can also only take one of 4 values: central, northeast, west, or south. So these are the values in the status and the region columns. Given that information, can we see what the cardinality here means? Again, if we're talking about the table cardinality, since we have 1,000 rows in the table, then the table cardinality is 1,000. Now let's look at the cardinality of each column. For the ID column, ID is the primary key. This means that each row has a different ID value. So this means that we have 1,000 different values. So the cardinality of the ID column is 1,000. For the date column, we have information that says we have around less than 10 orders per day. So if we do have the maximum, like if each day we have 10 orders, this will mean that each date is repeated 10 times-ish. So 1,000 rows divided by that will give us, 100 distinct dates. On the other extreme, if each date only exists once, this will give us 1,000 different dates. So the cardinality of the date is probably somewhere between 100 and 1,000. For the amount column, these are just money amounts, not very likely to find duplicates there. You might find some duplicates, but it's probably almost unique. So the cardinality here is also around 1,000. The status column, we know that you can only have one of those 3 values. So no matter how many rows in the table, you will always have only those 3 values. So the status column has a cardinality of 3. Similarly, for the region column, you can only have one of these 4 values. So the cardinality of that is 4. All right, now we've understood what cardinality means. Let's go back to bitmap indexes. So as I said, bitmap indexes is a kind of index like hash indexes or B-tree indexes, but this is a type of indexes that is designed specifically for low cardinality attributes. Why is that? Well, one, because they have a small number of distinct values, and we'll see what that means for us. The other thing is that the queries on these attributes usually are of the form of equality queries, like say where status equals approved, or it could also be in the form of like in lists. We'll see some examples of that. So you'll see a query like, find all orders where status equals approved. Or you will find a query that says, all orders where status in approved or pending. So this is basically like an or of two different status values. You might find a query that says, find all orders where status equals pending and region equals west. It is not likely that you're going to find a query that says, find all orders where region is less than west. It doesn't mean anything. Usually you're looking for a specific value or a list of values. Okay, so with that in mind, let's see how do we build a bitmap index on the status attribute, for example. So again, like go back to what I said earlier. Each index needs to map from an attribute value to the row IDs or to a way that will enable us to find the tuples. So bitmap indexes is the same thing. You want to map from each value to the rows that contain that value. And we do this by constructing these bitmaps. A bitmap is a sequence of zeros and ones, a sequence of bits. Each bit can be a 0 or a 1. So for each value, we want to have that bitmap that will tell us which rows contain that value. So if we're looking at the status column, we have 3 values, P, A, and D, pending, approved, and denied. So we're going to start with these 3 values and start constructing the bitmap for each of these values. We start from the top of the table, first row, and then we go over each row in order. So the first row, it has a P. I'm going to put a 1 in the P bitmap and zeros in the other one because this value has a P in it. Go to the second row. Second row has an A, so we're going to put 1 for A, zeros for the others. Third row has a D, so we're going to put 1 for D, zeros for the others. Same thing for the fourth row, D, so 1 for D, zeros for the others. And then A, so 1 for A, zeros elsewhere. So we keep doing that for every row all the way to the end of the table. So we end up with these 3 bitmaps. So for each value, we have a sequence of zeros and ones. The ones tell us which rows contain that value. This is basically all we need. The length of the bitmap is the size of the table, the number of rows in the table. We can do the same thing for the region attribute as well. So this time we have 4 different values. So we're going to construct 4 bitmaps, 1 for each of these values. Also, again, it tells us which rows contain that value. So let's go back to our queries and see how do we use these indexes. So again, if I have a query that says find all orders where status equals approved, I just need to get the bitmap for that approved value, get all the ones, and these will tell me which rows contain that value, and I can go and fetch these rows from storage. So as simple as that. If I have one of the more complex queries, like find all orders where status in approved or pending, so again, this is basically like an OR query. We're trying to get either status equals approved or status equals pending. So I need to get those 2 bitmaps, the one for approved and pending, and then do a bitwise OR on these 2 bitmaps. So for each corresponding bits, if either of them is 1, the result's going to be 1. If both of them are 0, the result's going to be 0. So this is the result bitmap of this bitwise OR operation. And basically, yeah, this one tells us about the rows that we need. Any bit that has a value of 1, I should go and get that row because it either has status equals approved or pending. The third query that we've seen, find all orders where status equals pending and region equals west. This time I need 2 different values from 2 different indexes. I can still go and grab the 2 different bitmaps, one for pending from the status index, one from west from the region index. And now I'd have to do a bitwise AND because the condition is an AND condition. So again, this means that for each corresponding bits, the result's going to be 1 only if both of them are 1s. So in this case, we only have 1 such case. So this is the only row that has both these values or both these conditions are satisfied. So again, knowing which bit is this, I can go and grab the corresponding row from storage. So yeah, this is basically how bitmap indexes are used. Now, let me go back to earlier when I said that this is designed for attributes with small or low cardinality. Why is that? Let's talk about the size of the index. When we were building the index, we built a bitmap for each value, right? So the length of the bitmap was the same as the number of rows in the table. So if we have a table with 1,000 rows, for example, then you have the bitmap has 1,000 bits, 1 bit for each row. 1,000 bits means if you divide that by 8, you get 125 bytes for each bitmap. Now, when we have 3 values, then we have 3 such bitmaps. So then the total size of the index becomes 3 multiplied by 125, or like by the size of the bitmap. If you have 4 values, then it's 4 multiplied by the size of the bitmap. The more values you have, the size of the index increases. So the size of the index is proportional to the number of distinct values in that attribute. So at some point, the index might get too big if you have too many values. So that's one thing. That's why we restrict it to smaller cardinality. The other reason is, the good thing about the bitmap index is that it's encoding a lot of information in a compact space. Like you have this bitmap that encodes the information about all the rows that have a specific value. Now, if you have many, many values, then the number of bits that are set to 1 is basically distributed among all these different bitmaps, right? So you have fewer number of 1s in each bitmap. The extreme case is that if all the values are unique, like if we were to build a bitmap index on the primary key, for example, then each bitmap will be all zeros except for 1 bit that has 1. So you have 1 bit that has 1 and all the rest are zeros. So this becomes much less efficient the more values that you have. The more values that you have means that you have fewer 1s in each bitmap. So it is less efficient to query. You're going to have to, to start working with multiple bitmaps every time. So at that point, it might be just, might as well just go and build the B3 index. It becomes, more efficient in that case. So again, good to work with that when you have low cardinalities. It doesn't have to be 3 or 4. Like it could go up to, 50 or 100 or something. But more than that, then it becomes debatable. And then like if you exceed 1,000, then definitely it's not efficient in that case. The next question is, what is the difference between attribute indexes and page indexes? Okay, so the terminology here is a little bit off, but I'll try to clarify this. So attribute indexes, I assume this is the kind of indexes that we've been talking about, like the indexes that map attribute values to row IDs, right? So like the database indexes that you create using create index and so on. These indexes are, like when people talk about indexes, this is the kind of index that we're talking about. These are visible to the user, created by the user. In some cases, they might be created automatically by the database, like in the primary key case, for example. They are visible to the query engine. The query engine uses them during optimization, during query execution. So yeah, these are indexes that are used for query processing, like by the query engine. And like I said, they map from attribute value or attribute values to row IDs. Now, the other type of indexes that this question is talking about when they say page indexes, I assume this is talking about some of the things that we talked about in the storage videos. Usually this is some structure that maps from row ID to location, like physical location where you can find the data. So row ID here is not the thing that you find in the index, this is the thing that you search for in the index. These are usually not something that's visible to the user. It's not something that's visible to the query engine. These are usually something that is internal to the storage manager component. Examples for that. Suppose that the row ID, like we've seen row ID in Postgres, for example, it has both like the page ID and the slot number. But in some cases, this row ID might not be as clear. Like this row ID might be something that looks more like a hash value, like like some just sequence of characters, like letters and numbers and stuff like that. That is not clear to see what the page ID is and the slot number is. So if that's the case, some systems may implement it like that. Then you need some structure to map from that row ID to the actual like individual components, like the page ID and the slot number. So this might be an index. And again, that will be maintained internally in the storage manager. The query engine doesn't know anything about that. It will just pass off a row ID and it will see a tuple coming back. It has no idea how this is done internally. Another example of that would be in the log structured pages, which we've also talked about. When we said that using a row ID, I want to retrieve the last entry that has that row ID, right? Because like each row ID might have multiple entries. And we said that one of the things to do that efficiently is to maintain an index that maps from a row ID to the last entry that has that row ID. So that's another index that can be internally used by the storage manager to efficiently retrieve that information. So again, these are all like internal structures that are maintained inside the storage layer. It has nothing to do with the query engine. It has nothing to do with the user. They have different implementations based on the system. Yeah, so that's the main difference. The next question is, what's better for performance? Composite indexes or using multiple indexes with index intersection, for example? I've already answered this question in the video about index intersection and union, but I'll go over it again, and also I'll link the video in the description so you can check it out for more details. As usual, there is nothing, unfortunately, that is always good or always bad. Everything has pros and cons. Everything depends on the particular situation, the particular workload, the kind of queries, the kind of predicates, the kind of conditions that you have in your queries. Depending on your situation, one solution might be better than the other. Also, depending on the implementation of how things like index intersection are done in a particular database system. So yeah, there's lots of factors that play into that. Again, each of them has pros and cons. So let's look, for example, the composite index first. Also, sometimes, in case you don't know, they might be referred to as compound indexes. So the advantage of composite indexes is, like, compared to index intersection, is that it's faster. It's much faster to query one composite index than to query multiple smaller indexes and then do an intersection on them. Because, again, I mean, you have to access multiple indexes, that's one. And also then you have to perform an additional operation like intersection on top of that, which can be expensive. So that's one advantage of using a composite index. Another advantage is that it makes the query optimizer, and this may not be relevant to most folks that are working kind of like on top of a database system, but like if someone is working inside the query optimizer and like develops query optimizer, then it makes the query optimizer simple. If all you want to support are composite indexes, then you don't need to consider plans that have combinations of indexes and all that. So that's another thing. Some of the disadvantages is that a single composite index can be larger than a single index on a single column. Also, if you have to create multiple composite indexes to support multiple different queries, then the number of indexes can grow a lot because you have to have these different combinations, like an index on A and B, an index on A and C, an index on B and A, because again, we've talked about prefix queries. So you may want to create all these different indexes, so the size required for index storage can grow a lot. And also, because you have all these different indexes, the cost of the update becomes much, much higher. Because as we've said before, like every time you update the data, you have to update the index. So when you have many, many indexes, then you need to update all of them, which becomes a lot of cost. It also does not allow for a lot of flexibility, as we've said, because you have to create indexes on combinations of columns, and if another query comes in that uses a different combinations of columns, so you cannot use that index, you need to create a new index. So these are some of the pros and cons of the composite indexes. If we look at the intersection of individual column indexes, the main advantage is, well, flexibility is one. You can create, let's say, index on individual columns, and then you can combine them in different ways to answer different queries. So you don't need to create like an index on A and B, and then a different index on B and A, and a different index on A and C. You can just create an index on A, index on B, then index on C, and then you can combine them in all different ways. So it gives you that flexibility. It also makes it so that you don't have to create too many indexes. You have only a few of them, let's say on single columns. So the space required for the indexes is much less. Also, the update cost is much less, again, because you have fewer indexes to update. The disadvantage is that it's slower. As I mentioned earlier, it's slower to query multiple indexes and then do intersection on top of that. So these are the trade-offs that we have to think about. So thinking about your own, let's say you have an application, you have a workload, which scenario do you choose? So I would say Composite Index would be a better fit if your workload is mostly reads and doesn't have many writes, because said, like, with Composite Indexes, writes can be expensive. So if you don't have that many writes, you don't have to worry about that part. If you are usually querying the same combination of attributes, like if most of your queries are, searching for, where city equals blah and, and date is less than blah. If most of your queries are like that, then just, build an index on city and date, and then you're done. On the other hand, when do you create, or like when do you use index intersection, assuming that the system that you're working with supports it and supports it in an efficient way? If you need the flexibility of querying multiple different combinations of attributes, like you're supporting like ad hoc queries or something like that, then you're probably better off with creating indexes on individual columns and relying on index intersection. Also, if you have a write intensive workload, if your workload includes a lot of write operations, then it's cheaper to update individual column indexes, fewer indexes, than having a whole lot of different kind of like composite indexes. So these are some of the things that you may want to think about. And again, it depends on your particular situation, which one will be better. All right, so this brings us to the end of this video. These are all the questions that I have received. I hope this helped clarify some of these points. If there are any other questions or anything that is not super clear, please add it in the comments and I will try to get to it as soon as possible. As usual, please hit the like button, share this video if you think it was useful, and subscribe to the channel to get all the updates as soon as they're posted. Other than that, thank you so much for watching, and yeah, see you in the next video.